thinking about, we have all of these systems on the landscape, and what does it do to water that we use and reuse as we move it through the system? Our efforts in this were really focused on nutrients. We have since started to look at some more pesticide movement with some collaboration with Cami Willett at the University of Arkansas. But this is some work that was done in an 80-acre field, so we're back to, back to the blue system again. So the reservoir is about 80 acres. There's about 700 acres of field, and about 97% of that water is retained within that system. So they lose, as I said, they lose a little bit of that of the surface water that they have on that system. So the yellow dots, the yellow shapes are sample locations. So we had 2 sample locations within the reservoir. We had what was coming into the reservoir, what was coming into the system here, what was leaving the system here, tailwater pit, and this going into this tailwater pit. So we had folks that were going out and pulling grab samples and analyzing them for the following constituents: nitrates, nitrites, orthophosphates, chlorophyll, total dissolved solids, total suspended solids, a whole host of things to kind of get a sense of what happens as water moves through these systems. So this is a more simplified version of what we've just looked at. So we wanted to kind of compartmentalize these into what's coming into the system. So 7 and 8 are in, out is 1, the reservoirs are 10 and 12, and then the pits are 2, 4, and 6. So, you measure it, and we saw really no statistical difference in all of these components from the what was coming into the system and what was coming out. We saw that water moving through the system didn't change these components statistically. We did see some differences in TSS and turbidity on what was coming in versus what was leaving the system. When we look at the system into those 4 components that I described, the ins, the outs, the reservoirs, and the pits, we saw no difference in this list of items here for nitrates, solids, temperature, etc. But we did see that water in the reservoir was significantly lower for nitrite and phosphates, and then also the reservoir had higher dissolved oxygen values. So we start to see that the reservoir water is some of the characteristics of the reservoir water is causing some changes in some of the water quality components, and what we like to see is a reduction in those numbers if at all possible. So, yeah.
So on dissolved oxygen being higher in the reservoir, is that what you expected to find, or is that? I'm trying to think of what effect that has.
Well,
it has more wave action in the reservoir.
Yes.
It's getting more oxygen.
We think that has a lot to do with what we were seeing there.
Okay.
Yes. Yeah. We really didn't know what to expect, really. Yeah. So we went in and everyone likes to say that these systems are retaining nutrients and reducing things, but what we saw from the difference between what was coming into the system and what was coming out, we didn't see that much difference. Mm-hmm. The only part where we started to see a difference is in that reservoir. Bear in mind, this is one system.
Yeah.
So we have since collected data on 3 different systems that are very similar, and we're working on understanding that data. But for the most part, we see that it's a neutral system. We see some reductions in what is being measured in the reservoir at this location. So moving on to the last section of recharge. So when I came to Arkansas, everyone's talking about the declines in the aquifer, and a logical response is, why don't we just put water back in it? We've got all this water in the spring. Let's just jam it back in there and see, why don't we just do that, right? And this was looked at in the 60s. It was looked at again in the 80s. And one of the primary conclusions from those efforts was that air entrainment in the recharge was going to cause a problem and not allow that to be an efficient system. They had a lot of sediment clogging issues. Basically, they were taking ditch water, putting it through a recharge well, and they had sediment problems. And then the biggest problem that I see is we have all of this surface water, but we have this confining layer of clay, right? So we need to get past that confining layer of clay to get water to where we really need it to go. The other challenge is the cost of water treatment. So 97% of the alluvial aquifer is used for agriculture. There are some communities that use the alluvial aquifer for their domestic water use. When that happens, the state requires that you bring any water that you're going to put back into the aquifer to drinking water standards. Okay, so that becomes really expensive, right? And so I want to talk on two areas from this slide: the access, and then the cost. And one of the things that I started to recognize as we were going through the countryside, we've got all of these reservoirs, and I'm a classically trained civil engineer, and why not use them as an initial sort of settling pond? If sediment is our problem, why not use the water in these reservoirs? Could we pull it off of the top? Could we use some sort of settling? Could we use these reservoirs as sort of an initial settling pond to then use that water as the source water for recharging back into the aquifer? So these reservoirs and tailwater recovery systems start to come hand in hand with this idea of what can we do to start to arrest or reverse this decline question. So there are a couple of different ways. Direct injection is one. I already talked about the drinking water standards problem, so this kind of takes it off the table for us in the agricultural context, right? It becomes way expensive and not something that we're going to be able to deal with. But managed aquifer systems, one that has passive movement through the saturated zone and then eventually into the aquifer is an option that we could explore. What we have to do is get past that confining layer of clay. That confining layer of clay is not a constant, right? It's variable. It's thin or non-existent in some locations, right? And so we're working to understand where that exists. So the idea is to use infiltration through the unsaturated sand as a filter before it goes back into the aquifer, but really understanding the water quality before it goes into that aquifer, into that infiltration gallery as well. So the confining layer of clay was defined by some work by the USGS in '87. Is that the reference? The USGS is currently, as we speak, working on understanding that system a whole lot better for some big modeling efforts that they're doing here in the very near future. So they are doing some geotechnical remote sensing to understand where that confining layer is and how thick it is. So we're hoping to get that information to then target areas where we could start artificial recharge projects to kind of get a sense of what are the components we would need, how big would they have to be, those kind of things. What is the change as we put one in this location, monitoring wells around that area. So the idea is to use that work that the USGS is doing now to get a sense of where those locations might be, where we could target this practice. So this project that just looks like a big pit. We affectionately call it the pit. Was just that. We had a collaborator, producer call me up one day and he said, I've got this big hole. They're collecting, they're taking sand out of my farm for some highway project, and they're going to fill it back up, but could you do something with it while it's open? And so you can see the confining layer is like right in here. Okay, so it got past that confining layer and got into the sand. Okay, so we figured, okay, well let's test it out. Let's see how quickly could we move water through this system, and that's what this data show on the left. We moved the surface water, which is shown here, from a small bayou nearby through some poly tubing, and then that was right here, and that was pumped for believe 24 hours, don't quote me on that. And then we start to see, and we instrumented the heck out of this pit with pressure transducers, precipitation, weather station, trying to get a sense of where this water is going and how it changes. So we saw the water going into, so the blue line and the red line are pressure transducers. This is water level depth in the pit. This is after we stop pumping, and then we see a precipitation event, and then we start to see this decline, precipitation event, and we start to see the decline. And then this is the black dashed line is another staff gauge nearby. So this tells us that water is going into, it's leaving the pit. We had minimal monitoring in the surrounding area, but we feel like this is an opportunity for us to, at least, it allows us to understand that it's possible. We have some numbers associated with that infiltration, and we hope to move to some more pits here in the winter season with some collaboration with the NRCS to try to get some better numbers associated with this project. Yeah.
How deep was that clay layer?
At that point, it was, I believe, it's about 10 meters.
Oh, so
it's pretty deep.
It's pretty deep.
Yeah.
Okay.
Yeah, it's pretty deep. It's pretty deep. And so, you know, it's interesting, the work that was done by the GS in the late 90s, where they think the confining layer is and how deep it is, the depth to the confining layer is just weird and so variable that it's hard to predict. So that's the part about how to get the water in. This is the part about what kind of water quality are we going to have if we use tailwater recovery reservoir systems as an option for source water for recharge. Okay, so this is a project we looked at. These 6 reservoirs, all varying years of construction and size and vegetation. This was some work that Clarissa Cahill, a graduate student of mine, did her master's thesis on. So I've just pulled out some points about it that I thought would be of interest. So we really focused on the dormant season. We're not about to ask folks to do anything more during the production season. This is a question of when we have surface water, how can we move it to a place where it's going to get back into the aquifer. So we collected from October to April in 14 and October to April in 14-15 and then 15-16, basically doing grab samples on surface water and then low flow methods to collect some well data as well. Because the idea is, you know, we want to understand the differences between the water quality in what we're proposing one might put back into the aquifer to understand what's actually in the aquifer now. Okay. So pretty standard lab analysis, nitrites, phosphorus, turbidity. We also looked at a bunch of metals, which I'm not going to get into the details of that. The short story is that there wasn't much in those systems. So to move toward the results, turbidity and TSS concentrations were lower in the reservoir compared to the ditches, right? So going back to that 60s work that was done by the USGS, they're attempting to take ditch water and pumping it back into an injection well. They clogged up those screens pretty quickly, and so that really plays out here. Those reservoirs allow the turbidity and the TSS to go down to levels that we think would be more reasonable to use for recharge. Phosphorus and nitrate concentrations were also lower in reservoirs compared to ditches. Again, we want to understand the components and the constituents of that source water before we introduce it into the aquifer. So then the question is, well, when would be a reasonable time to do this? December, January seem to be the best times from the work that Clarissa was able to pull together. Lower inputs during the dormant season, some settling of suspended solids in the reservoirs, and weather was a big part of that question. So we talked a little bit about the USGS. To summarize our work in recharge and how it relates to reservoir tailwater recovery systems, we're trying to figure out the best places to try to test this recharge question. And so you might think, well, why don't we use reservoirs? That's what some folks have suggested. So reservoirs can't at the same time be used to store water and then be used to be filters to move water back into the aquifer. That's just asking them to act like two different animals at the same time. So we, in a perfect world, we would have a system that has a reservoir and nearby a location where the depth to confining layers is relatively shallow, and we could move water from the reservoir into that recharge area. We saw some promising data from potential sources by using the reservoir from a water quality perspective. As I said, we're moving toward understanding some of the herbicide and pesticide components of that source water, which we're doing now, and we're really moving away from direct injection and trying to focus our efforts on passive artificial recharge through infiltration. All of this work is done in collaboration with a whole lot of people. First and foremost, the producers. The DAB said it well today. They're willing guinea pigs, and without them, we would not be able to do most of the work that we do. If you've noticed, the work that my unit does is about 95% of it is on farm, which has its challenges, but really we believe that it's the space and challenges that will benefit producers in the end. So we have a really nice collaboration within our CS. We're entering into an agreement to start to look at some of the planning questions. Where should we put these reservoirs? Where should we put some of the different tools that we can use to start to improve water efficiencies and, again, reducing the decline in the aquifer. So to summarize, we use these systems to offset groundwater pumping, right? We have this beautiful source for irrigation. And if we continue to mine it as we have, we're not going to have it for as long as we would hope. Reservoirs need to be protected against erosion, be it through artificial sources, be it through better planning and design. But we need to think about that as we're at the design stage of where should we put these systems and how should they be organized. And then I think the other thing that we haven't spent too much time thinking about is within a watershed. The DABs today talked a bit about we used to be the only pump on this ditch, and now there are 40 between us and Stuttgart. So if we start to put these systems out, we need to think about where are we going to put them and how are we going to put them so the people that are at the bottom of that ditch aren't without water. From our initial work in water quality with reservoir tailwater recovery systems, those systems are basically neutral. We don't see major increases or decreases in the water quality components that we measured. We do see reduction in what's coming out of the reservoir. And I really see these systems as an opportunity for using them in concert with some work with artificial recharge to help us improve our water resources in the state. So this is my contact information. If you have any questions, I'm happy to answer them.
So you have, and you don't have to give me an exact number because I won't remember it, but I was trying to visualize the relationship between the reduction in the aquifer annually and what that number would be that we have to put back in to reach a neutral level. Is that ever attainable?
So what happens when the aquifer loses water?
Mm-hmm.
So an aquifer is made up of rock, soil, air,
Mm-hmm.
and water.
Mm-hmm.
Right? When you remove the water, it will start to compress, and its capacity to hold water
Yep.
will be reduced. So we're never going to be able to go back to where we were because of that loss of void space.
Mm-hmm.
We need to do something. I don't have a number for you.
Well, like I said, I didn't really know. I
Okay.
was just looking for a relationship there.
Mhm.
Obviously, what you're talking about, as that aquifer loses its capacity to hold water, theoretically, the surface of the earth is moving
Mhm.
further from the sun too. Maybe not significantly if you use that measurement, but it'd be good if we could stop it here and fill
Absolutely.
it back up at the current capacity and reuse it just like we use
Absolutely.
it. But I just wondered what the reality of doing that was.
Yeah, we've got some kind of back of the envelope numbers, but which I'm not prepared to share. But I think that's why I say arrest or reduce the declines. I think we have an opportunity to have an impact, but and it's not going to happen only with recharge, right? It's going to have to happen with conservation practices and technology and starting to use less, but continuing to sustain yields. We've been looking at a lot of different practices that if it starts to impact yields, it's not a practice we really want to get into, right? We may, heck, you can grow rice without water if you wanted to. But you're not going to be able to be in business for very long. And so it's this idea of putting practices on the landscape that make sense across the board by sustaining or improving yield, but basically using your resources more wisely than you would otherwise. So, yeah.
Any relationship between high water years, the flooding of all of our rivers,
Mhm.
and the recharge?
Mhm. I don't have it in here, but if you look, I usually use this slide, but I didn't put it in here today. There's some data from as late as the 30s, right? And it's in the Grand Prairie, and when we have high water years, we feel like we get back up to where we were. But over the course of time, from 30s to now, there's a consistent decline in those levels, right? So we're coming back up, but we're not coming back up to where we were in the 30s, right? So it's been. I'd like to use my hands, but if you start here in the 30s and if you were to track the water depth, it would come down during the production season, then it would come back up, but it usually doesn't come right back to where it was. And then it comes down, then it comes back up. And some years it may go back up to where it was, but over the course of time.
Lower lows and lower highs.
Yes. Yeah. I have that image. I have those plots because they really are very telling. Because we've been tracking water level around the Jonesboro area, and yeah, when we have wetter years, we do see a really nice recovery, but compared to where we were in the in the 70s, we're still a little lost. Okay, thank you.
Thank you.